Hello, Tanya Laird here, and welcome to part 2 of lecture 13 of ENGR 231 Engineering Statics. This video is hopefully going to be a bit shorter than the previous one. The previous one was quite long indeed, at least for as this lecture series goes. There are some courses that I have, even longer videos, but this one I've tried to keep them short. But that previous one was a bit of a doozy. So, in this one, we're going to look at the relationship between V and M, between load, shear, and moment, in terms of the calculus or the derivative and integral relationships. So load, shear, and moment. Derivative and integral relationships. And this is going to be continuing on what we discussed previously, or in the first portion of this lecture. Integral, not interval. Integral relationships. So that'll be the title of this video, or some variation therein. Lovely straight line. Okay, so as we saw previously, there is a calculus-based relationship between these things. And we can think of this a few ways. First, we can think of it we can see this a few ways. First, we can see this from the actual functions that we go and solve for, that we've actually solved for using the method of sections. So this method here, we take it in cuts and do method of sections, etc. on it. And so we can see that this is that the shear is the derivative of moment, and moment is the integral of shear. And same thing here. Another way to think of this is that if you actually find the area under this curve, you will find that it equals the change in from here to here. So think about this. This is a trapezoid. This is a trapezoid that goes from negative 6.5 to negative 18.5. And the formula for the area of a trapezoid is the average of the two bases times the length. So that would be 4 times negative 6.5 plus negative 18.5 divided by 2. And that would come to, well, is that not quite right? Negative 18. Oh, not negative 18. Negative 18.5 there. And that comes to what I would expect it to be, which is negative 50. So the area of this thing is negative 50. And what this is going to tell us is that there are, in addition to the, well, actually not in addition to, but precisely because there is an integral relationship, there is a area relationship between these as well. So in other words, the area under the shear function will give us the change in the moment function between 2 points, and the area of the again, the area under the shear function will give us the change in the moment function between 2 points, and the same thing between the load function. So I'm going to define 3 functions, or list 3 functions. W of x is going to be any distributed load function. Any distributed load function. V of x is going to be, oh, I should probably note, this only describes your actual distributed load. So we're looking for load functions like this, some sort of W of x. It can be as complex as you want, but it really does have to be a function. W of x's are not going to be point loads. They are loads as a function of x. These would be discontinuities between your zones of analysis, but you can't really integrate across a point. That concept doesn't really make sense. And so that's kind of out for W of x's. For W of x's, we're talking about purely integrating across a function, or we're talking about a function that is continuous across at least some region of the beam. It's not going to have to be continuous across the entire beam, but at least some region of the beam. V of x is your shear function. And M of x is going to be your, M of x will be your moment function. And the relationship between these are as follows, the calculus relationships. V of x is going to be equal to the negative integral of W of x dx. It's going to be equal to the negative integral of W of x dx. And why the negative? Well, this comes down to 2 things. Well, actually, I should probably also list the derivative relationships. W of x equals the derivative of V of x. I'll come back to that, the previous thought in a second. dv of x dx. So so the load is equal to, I need my negative there. Load is equal to the negative derivative of shear, and shear is equal to the negative integral of load. Now, as for why that is, well, it all comes down to this. We like to define this type of loading as positive. We tend to like to say that, well, basically where that comes from is we like to have two things. Maybe I can do a little bit of a note here. You know what, maybe I'll save that for, I'll finish out the thought on these. Then I'll talk about that one. I keep jumping around, sorry about that. M of x is equal to the integral of v of x as a function of x dx, and then v of x, the shear, is equal to the derivative of moment as a function of x dx. So in other words, shear is the derivative of moment, load is the negative derivative of shear, and vice versa. We can also have the integral relationships. So a common question I always get is, what's with the negative? There's negative on the relationship between shear and load, but there's not a negative between shear and moment. And the reason is fundamentally because of this, our choice of sign convention on two things. We want two things to be positive, and honestly, these are kind of contradictory. As engineers, as practicing engineers, or as, well, this is, I shouldn't say we, I mean, this has been the sign convention for generations. This probably goes back to 100 years or something like that. This is very old sign conventions. Just like kind of positive, negative charge in electricity. They defined positive charge before they knew that it was electrons moving around, not protons. But yeah, so you define, in classical analysis, circuit analysis, you define protons, or you describe the flow of positive charge, even though protons don't really move around in wires, electrons do. But anyway, it's kind of like that, well, except not as contradictory, I suppose. But anyway, we want to, back to this, we want two things to be positive. These things are somewhat contradictory. One, downward loads. Again, because this is mainly because, again, as we saw in a bit in lecture 12, we like to have downward loads. We like to have, or we deal with loads, at least civil and many mechanical engineers deal with downward loads a lot more frequently than they do upward loads. So we want this to be a positive W of x on a beam that you're analyzing from left to right. W of x is positive downward. So if you have a load, a W of x that is acting downward, we refer to that as a positive load. So we want downward loads to be positive, even though intuitively it might make sense for, you might think, oh, upward thing, that means it's, if the force is going up, that would mean that would be a positive load, right? Nope. By our definitions, if the load is going down, it's positive. And the other thing we want is we want the load produced by downward load, or the bending produced, or the deflection produced by downward load, or maybe the moment. Or I can just say the bending produced by downward loads to be positive. Produced by downward loads to be positive. And this was discussed previously. This was discussed previously in lecture 12. So in other words, if we have our same distributed load there, maybe I'll just show a point load for simplicity. If we have a downward load, we want to define this type of bending as positive bending. Again, just because that's the type of bending you encounter in the field, and in real design cases a lot more than you encounter upward bending, although you certainly do have those sometimes. In fact, our beam here, with its negative bending moment, is actually one where you would have that. This would be from the previous lecture, that would actually be a case of that. The beam, if you were to actually draw out the deflected shape, this is the original shape here. Its deflected shape would end up being something like this, concave down throughout, like that. But anyway, so we want these two things to be positive. Or we want both downward loads to be positive and a downward bending to be positive. And just the way the math works when you start working through the derivatives and integrals, the only way that works is if you tack a negative onto the shear. You could get away without having that if you were if you were content having a upward load to be positive or a downward bending to be negative or something like that. But if we want moment like this to be positive and we want downward load to be positive, we have to have that negative there. It's absolutely essential if you want the math to work out. There's no other way to make the math work out. So it's kind of just a kludge. It's not something that you can really derive from base principles. It's not like, you sat down with it's not like you sit down with, a physics textbook or just the Principia Mathematica from Newton and just derive from base principles. Oh, this is the force in beams, and the negative just pops magically out of the math. No, this is just because we like this to be positive and we like this to be positive, and so we need to add a negative to make all that balance out. Okay, so that's all well and good. But if you want to, so what can you use this for? So that's nice, but what is this beyond trivia? Well, you can use this. Can use integral relationships to determine the shear and moment functions. To determine the V and M functions. And this is especially important, very important, when, let's say, the load is complex. The load is rather complex, and not necessarily complex in the sense that there's a whole bunch of different zones and discontinuities and things like that. That's actually done best by the method of inspection, which I don't know if we're going to touch on this semester. But when I say complex, I mean mathematically complex. Like if you have a nice constant value load, method of section is probably the best. If you have a linear load, well, even method of sections there is pretty decent. But if you have very complex loads, like I gave you a sinusoidal load or something like that, that would be a pain in the butt to do via method of sections. So would be a lot more easier to deal with via integration. Now, because we're dealing with integration, we have to remember some things from calculus. And in particular, we have to remember that some things from the fundamental theorem of calculus. In the previous slide or two, I actually lied to you. Well, not directly, more of a lie of omission. The fundamental theorem of calculus. I told you that shear was equal to the negative integral of w of x dx. In reality, that's not actually the case. It's mostly the case, but if you really work through that integral, what you really end up with is that constant of integration. Remember that horrible plus c that you always have to add to integrals? Or actually, I should probably say that plus c will just come out of the integration. When you take the integral, you're left with the plus c. When you take an indefinite integral, you're left with this. So what this really tells us is that you'll always end up with that horrible plus c, that boundary condition that you get in differential equations. And so remember that plus c is what's always going to come out of this. This is the infamous plus c that is the bane of every freshman calculus student. It's kind of a rite of passage, I think, that every single person who takes calculus has to bang their head against the wall and just repeatedly always forget to put on that stupid plus c. And that it's almost inevitable at the first integration exam, when you first learn integration, you'll be forgetting that plus c, and you lose like 3 stupid points because it was so easy and you knew you were going to do it, and you do it every single time. Anyway, I'm not venting. Okay, I've been apparently traumatized by past experiences of not having plus c in exams. And I took calculus quite a long while ago. Oh boy, I feel old now. Okay, so v of x is equal to this. But when we take this integral, we actually get a plus c. And so the v of x is not actually directly equal to the integral of c of this. Expressed in a little bit different form. If you actually want to do this in a more exact form, I could say the shear at point B minus the shear at point A. In other words, if you have a beam with some distributed load on it, and then a point A and a point B, the integral of the load function is not going to give you the exact values of the shear. Rather, it's going to give you the change in the values of the shear. is going to be equal to the negative integral, or just the integral a to b of negative w of x dx. So if you're doing this in definite form, then this will not tell you the exact value of the shear, rather it will tell you the change in shear between these 2 points. So that would be one approach, or another approach is to actually solve for c, do the integration indefinite, get the c, and then put back in boundary conditions, which is what we're going to do. And then I could also say the same thing for moment. Moment of x is not equal to the actual, it's kind of not really true, it makes sense mathematically, or to write it out mathematically, but it doesn't exactly give you, if I have the shear function, I can't just take the integral of it and get the exact moment function. Rather, what I need to do is I need to realize that the change in moment between 2 points is going to be equal to the integral between those 2 points of the shear function, v of x dx. So you can do it this way if you are only interested in the change in shear, the change in moment between 2 points. All you need is that original function. But often what we're after is the complete moment function and the complete shear function. And to get that, we need to use boundary conditions. Boundary conditions are points of known shear and moment. Are points of known shear and moment. And moment. And I can talk about a couple of these. First of all, let's look at shear. Shear here. Basically, one thing to keep in mind is that at the start of a beam, let's say you have a beam like this, and you solved for the reactions and found that this is 10 kips here and 5 kips here. Immediately, I know that the shear diagram, I don't care what the load function is doing here, some arbitrary load function between these 2 points, but with reactions of 10 and 5, I immediately know that on the right-hand side of the beam, the shear is going to jump up to 10. Basically, point loads cause jumps in the shear diagram, which means I'm going to be at 10 here, and then I'm going to be down at negative 10, or negative 5, sorry, here. This is the v as a function of x. So I'm going to start up at 10 here, and then I'm going to have some change in this. Generally, the shear function, you would think that this would have the opposite relationship, where a jump in this would cause because these are external forces, and this is a diagram of internal forces. So I would normally think that this would be start downward at 10, but we have that negative baked into the equation. So one simple way, so then there would be some shear function between those. But the general thing to keep in mind is, if you have a beam, a good boundary condition is that if you have and this would be, for example, a simply supported beam. If you have a upward reaction of 10 kips on the right, or sorry, on the left, it's going to start out at 10 kips, and basically this comes from point loads or reactions causing jumps in the shear. And so if you have a jump on the right-hand side of 5 kips, you know the thing has to come back to 0 at the end, and so your final value of your shear is negative 5. And then moment, and this would be true whether this was a cantilevered beam, or so let's say you had a simply supported beam here, 10 kips and 5 kips, but if you had a cantilever beam and you knew its shear on the left-hand side, or its AY or something, was 50 kips, you would know its shear diagram would start out at 50, and then through some sort of function, it would have to end back out at 0 if there was no point load at the end. If there was a point load at the end, it could have something that would bring it back down to 0, but if it's just some function, it's going to, that's your w of x, it must come back down to 0 unless there's a point load at the end, or basically at the end it always comes back to 0. It's just from the matter of the end point load will be what does the final jump to bring it back to 0. So anyway, you can think of end reactions as one source of boundary conditions, at least, and those work really well for shear. Moment, a common boundary condition, is going to be pin and roller supports. So if you have pin and rollers, if you have pin and roller supports at those locations, the moment is 0. Wherever you have pin and roller, the moment is 0 there. And if you have a cantilever beam, and that's simply because by definition they cannot resist any moment, and so the internal moment there must be 0. If you have a cantilever beam, well, actually I should mention that's the pin and roller at the ends of beams. Here we had a pin support here, but the moment was not 0 there. In fact, it was actually maximum. Roller support at beam end. At beam ends, moment is 0. And cantilever beam, if you have a cantilever beam like this, with some W of x, and then an M of x here, your moment diagram is going to start at basically negative M of x. There's the, again, this is we're applying a counterclockwise force, or a positive moment to the outside, and the moment diagram describes the internal force, and so that would be a negative. So you'd have some negative moment, and then it would come back up to 0 as you get to the end. Okay. Finally, I need to mention zones of analysis on this. How do you handle multiple zones of analysis? Zones of analysis / discontinuities. We're going to need to use boundary conditions for each zone of analysis, but the problem is our boundary conditions must come from that zone of analysis. Boundary conditions for a zone of analysis must come from that zone of analysis, or the section of the piecewise function. Must come from that zone of analysis. So this produces a problem if you have something like this. Imagine you have a beam like this here. So you have a distributed load here, some distributed load. And in fact, I might actually work through this one. This one's going to be simple enough that I think I can work through this. Basically, the idea is that you will use one end zone of analysis, or use the end values of one zone of analysis as the boundary conditions of another, of the next. I think that'd be a good one because that's relatively simple to integrate. I'm trying to keep this lecture a little bit shorter than the last one, or quite a bit shorter actually, or this portion of it anyway. Boundary conditions of the next. So let's put this all together in an example. So we're going to have a beam, consider the beam below, or given. So let's say we have a simply supported beam. And let's say there is a moment on this thing, or not a moment, a load of, oh, I don't know, let's say 3 kips per foot. And here, actually, you know what? Let's make this interesting. Let's make it something we actually would want to integrate. Let's say this is a triangular load. So I'm going to start at 3 kips per foot, and dimensions. Let's say this here is maybe 4 feet, 6 feet, and 4 feet. This is given, and then find the V and M functions of this beam, the shear and moment functions of this beam. And I'm going to approach this from a very mathematical, calculus-based approach. So the first step is going to be to solve for the external reactions. And I'm just going to go ahead and say there's going to be an AY here and a BY. And let's see, I can do a summation of moments about point A. So solution here. Summation of moments about point A. I will have first BY, the negative moment or the positive moment caused by that, BY times the moment arm length of 14 feet, and then minus the equivalent point load of this. It's a triangular load, so it's 1/3 from its edge. So that's going to be 3 kips. That's going to be an area of 1/2 base times height. So 1/2 times 3 kips per foot times a length of 6 feet, or just 9 kips. And this is going to be a distance of, from the end here, this will be a distance of 4 plus 6/3, or 6 feet. 4 plus 1/3 of 6, or 6 feet. And so then minus 9 kips, again the moment about A, this is clockwise, so negative. 9 kips times the moment arm length of 6 feet equals 0. And so BY is equal to 9 times 6, or 54, divided by 14, and that then comes to 54. Let's see, do I want to do this in ugly decimal? No, I'll go ahead and do this as exact form. That's always nice when doing it by integration. Let's see, let's do that exact. And that would be just 27, oh, I could have just done that in my head. 27/7 kips. So that's the reaction force on B. And then I can do a summation of forces in, or summation of moments about point B. And I would have AY, or negative AY, times moment arm length of 14 feet. And then plus the 9 kip force. And now times the moment arm length of, well, it's going to be 4 feet plus 2/3 of 6, so plus 8 feet altogether. 8 feet, and this comes to 0. And so AY is equal to 72 divided by 14, or that would be 36 divided by 7. And if I added those two up, let's see, 36 plus 27, that would come to 63. 63/7 is 9, so those do add up properly in terms of summation of forces in the vertical direction. So we have AY and this. So let me go ahead and redraw this Rubai diagram over here. Let's see. So on support A, I have a reaction of 36/7 kips. 36 divided by 7 kips. I'm gonna like this. Maybe I'll make this a bit longer. And then at B, I have a reaction of that again was 27/7. 27/7 kips. And then in the middle, I have my triangular load. Like this, triangular downward. And the lengths on here, the dimensions are 4 feet, 6 feet, and 4 feet. So what I'm going to need to do is I'm going to need to get a, first I'm going to need to acknowledge that my boundaries of analysis, I have discontinuities here, 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 and here. Here because of the end of the beam and a reaction, here because of a load starting, here because of load ending, and here because of a point load and a end of the beam. So my beam boundaries or zones of analysis are going to be 1 when x is between 0 and 4 feet, 2 when x is between 4 feet and 10 feet, and 3 when x is between 10 feet and 14 feet. again, we're keeping, just like we did last time in the first portion of the lecture, we are keeping our coordinate system constant. We're putting 0 on the left-hand side and just x to the right positive. And so what I mean by feeding one into another, as I mentioned previously, or as I mentioned in terms of boundary conditions, we are going to use the boundary conditions on one of these into the feeding it into the next as we go through these. But the first step is going to be perhaps to get w of x. And w of x, I'm going to say there are 3 parts: w1 of x, w2 of x, or w2 of x, 1 of x, and w3x. Or I should say of x. 3 of x. And this one again is when this is in the first zone, the second zone, and the third zone. So the first thing is fairly straightforward. W1 of x, well, that's just 0. There is no distributed load between x equals 0 and x equals 4 feet. Same thing with W3 of x. That is going to be just 0. Now, we need to use some basic algebra to get this one here. Basically, I'm just going to use, I know that's a linear function, so I can just apply what I know from literally, algebra or pre-algebra, and say I have known points of 4, comma, oh, I forgot the number there, that was 3 kibs per foot. We want a linear equation to describe this, so I have two known, basically I have an ordered pair here, 4, 3, and another one of 10, 0. And I remember my basic algebra, so I can find the equation of that line. The m, and that's just rise over run, is going to be -3 over, well, the rise is -3 from here to here, and the run is 6 feet long. So this is then -1/2. The slope is -1/2. And that would have interesting units of like kibs per foot squared or something like that. Kibs per foot per foot. But I don't necessarily write all these out with their numbers or their units. Then I need to get the b, the intercept b, and y equals mx plus b. So y equals -1/2 x plus b. And then a known point, I could use this. 0 equals -1/2 times 10 plus b, so b equals 5. So y then, or in fact w of x, w2 of x, is equal to just -1/2 x plus 5. -1/2 x plus 5. And so then I could say w of x is equal to 0. We should probably double check that. If I put in 4, I will get -2 plus 5 is 3. If I put in 10, I will indeed get 0. So our function does check out. So our piecewise function then, let's see, is going to be, our piecewise function is going to be 0 when x is between 0 feet and 4 feet. It's going to be -1/2 x plus 5, -1/2 x plus 5 when x is between 4 feet and 10 feet, and then 0 again when x is between 10 feet and 14 feet. And we now have our complete load functions. This is very common to have zeros, especially if you have if you don't have load over your entire beam, then you will definitely have zones where the load is actually 0. Okay, v of x. Now that I got these, let's see, how might I want to do this? I might actually want to break these down into zones 1 and 2, or zone 1 and 2 and 3. So I'm going to next look at when x is between 0 feet and 4 feet. So 0 to 4, well, I know that v of x is equal to the negative integral of w of x dx. And I should probably say, to be consistent with what I've done previously, v1 of x is equal to the negative integral of w1 of x. However, this is just the integral of 0, so that's just the integral of 0 dx, or just a plus c 1-1, maybe I'll do. Maybe c11 for the first constant in integration in zone 1. So what can I do for that? Well, I need a boundary condition. So basically I know that v1 as a function of x is just equal to c11, and a boundary condition is that basically here in this first zone I know that initially the shear is going to do this kind of thing here, where it's going to pop up. And so I know that V, the boundary condition I can use, V1 at x equals 0, is going to be 36 over 7. And so that means that V1 as a function of x is just 36 divided by 7 kips. So the negative doesn't actually apply here, doesn't actually make an effect, the negative term. Then m1 as a function of x is going to be the integral of v1 as a function of x dx. And so that's going to be the integral of 36 over 7, not 36 over 7 at x, but just 36 over 7 dx. And that will come to 36 divided by 7x plus C12, maybe the first or the second, we're in zone 1, but it's the second constant. And I need a boundary condition, and this one's fairly easy. I know there's a pin support over here, so as we discussed, that means the moment is 0 there. If you ever have a pin or a roller at the end, either end of a beam, that means the moment there is 0. So I can say that m1 at x equals 0 is 0. So if m1 of x equals 36x plus c2, that means, or c12, that means c12, the constant on zone 1 in the second constant, is going to be equal to 0. And you don't need to use these subscripts. I know these can be confusing. I'm just trying to make it so I have unique labels for each of my constants in this problem. But that's somewhat of a style choice. So that would mean that m1 as a function of x is equal to 36 over 7 times x. 36 over 7 times x. So I have my v1 and my m1. Next, I want to look at the zone from 4 to 10. X is less than 4 feet, or is greater than 4 feet, but less than 10 feet. Here, w of x is what I found previously, or w2 of x is equal to negative 1/2 x plus 5, negative 1/2 x plus 5. And that's going to be, well, then I can say v of x is equal to the integral of negative, maybe if I want to be consistent, v2 of x is equal to the negative integral of w2 of x dx, and that would be the integral equal to the integral of 2, or just 1/2 x minus 5 dx, putting the negative in, and then that would come to the integral of, or I want to take the integral, 1/4 x squared minus 5x, and then plus, I'm going to call this C21, the coefficient in zone 2, the first coefficient in zone 2. So we have another constant of integration, and I need to use a boundary condition, or I need to find a boundary condition. However, I can't use this boundary condition here. I can't say that, oh, the shear here has to be equal to 36 over 7 kips, and then just put in, try to put in an ordered pair of 0, 36 sevenths. That's not going to work because we have a different function for the load here, and the shear here. So I need to find a boundary condition that is in that zone. And at first you might think, oh my god, there's no supports, I'm screwed, I can't do that. Well, you do have one. The boundary condition that you can use is relating one zone of analysis to another one. As long as there are no discontinuities in the load, well, actually I should say sharp discontinuities, mainly point loads. A point load will cause a sharp change in the shear diagram, but again, a point load will cause a sharp change in the shear diagram, but a distributed load will not. So what I can say is the boundary condition is that v2 at x equals 4 is equal to v1 at x equals 4. And v1 at x equals 4 is the same as it is anywhere, and that's 36 over 7 kips. So basically I can say 36 over 7 is equal to 1/4 times 4 squared minus 5 times 4 plus C21. So that's just going to be 4 minus 20. because that's just basically 4, and then minus 20, and then so basically 36 over 7 plus 16, and C21 is equal to 148 divided by 7, if I managed to math that correctly. And so then V2 as a function of x is equal to 1/4 x squared minus 5x plus 148 over 7. And then I can get moment, and m2 of x, assuming I've mathed this correctly, is going to be equal to the integral of this. So we'll have a cubic function for a moment. Isn't this fun? Is going to be, let's see, the integral of that will be 1/12, I should probably actually write it, the integral of v2 of x dx, which will be equal to 1/12 x to the third minus 5/2 x squared plus 148 over 7 times x. Times x. And the boundary condition is going to be the same kind of thing. It's going to be balance of moments. Basically, the boundary condition, m1 at x equals 4 must equal m2 at x equals 4. And so I can just use that. And I want to calculate the moment at x equals 4 for this first zone. So I'm going to substitute that into the equation here, 36 over 7. 36 over 7 times 4, that's the m1 as a function of x with 4 substituted in, is equal to 1/12 times 4 to the third minus 5/2. Oh, and of course I'm going to have my constant, which I would call C22, the second constant integration on region 2. 5/12 times 4 squared plus 148, and I'm just going to throw this in my calculator and let it chug on the fraction, times 4 plus C22. So 4 to the third divided by 12, and then minus 5 times 4 squared divided by 12. Does that make sense? Oh, no, that is a typo. That should be 2, not 12. 5/2 x squared. One of those things. So 5 times 4 squared over 2 plus 148 times 4 divided by 7. So 4 to the third over 4 to the third over 12 minus 5 times 4 squared over 2 plus 148 times 4 over 7. You can see this does tend to get a little bit ridiculous at times. And C22 then would be equal to, if I want to do this in exact form, which I am, 1048 over 21. So m2 as a function of x is then going to be equal to 1/12 x to the third minus 5/2 x squared plus 148 over 7 x plus 1048 over 70 or over 21. 148 over 7x plus 1048 over 21. And plus there. So we have that. Let's see. So we now have our this is going to be really as hard as it gets. That's our hardest moment calculation. Now I could use the boundary. I could use these as boundaries feeding into the next one, but I think I'm probably just going to use the right end of the beam as boundary conditions because these are pretty hairy equations. Well, not necessarily. They're just tedious. Then the final zone is going to be when x is between 10 and 14 feet. And so my w of x in this case is just going to be equal to 0, and v of x is equal to the integral of negative w of x dx, which will just come to I would call this C31. Well, I should probably say this is the integral of 0 dx, which would simply come to a C31, the first constant integration in zone 3. And I need a boundary condition. And that boundary condition is, remember back here where I talked about if there's an upward force here, this would be the negative version of that, like negative 5 kips. So I know the reaction over here is 27 over 7 kips. So that means the boundary condition I can use is V at x equals 14 is going to be equal to negative, because that 27 over 7 is going to bring this thing back to 0, but the very instant before that, it was at negative 27 over 7. So negative 27 divided by 7 kips. And so therefore, now maybe I could put a W3, V3, W3, or V3. So V3 is a function of x is going to be equal to negative 27 over 7 kips. Then M3 is going to be equal to the integral of V3 of x dx. And the integral of this, very simple integral, is going to be negative 27 over 7 times x plus, I'd call this one C33, the third constant of integration in zone 3. And I need a boundary condition. And I know at the end of this beam there is a roller, and that means the moment there is going to be 0. Again, if you have a pin or a roller on the ends of a beam, the moment at those locations are always going to be 0. So I could do this kind of thing here, where I could set, I could say the moment in zone 2 at x equals 10 must be equal to the moment in zone 3 at x equals 10, but it's late enough at night already. I'm just going to go ahead and be a little lazy and say that m at x equals 14 is equal to 0. So then I can say 0 equals negative 27 over 7 times 14 plus C33 is equal to 0. So C33 is equal to, that's just going to be, let's see, that's 27 times 2, I suppose. So that's just going to be 54, yeah, 54. 54, and that would be units of kip feet if we wanted the units. And that should say 3, etc. So then M3 as a function of x is going to be equal to negative 27 over 7 times x plus 54 kip feet. And then I might want to summarize these. Since I already got the w of x as a function of x, I don't need to, or in full piecewise form, I don't necessarily need to write all those out. But v of x would be equal to the following. Let's see. In the first zone, actually I may just write both of these. And one thing, let's see, when x is between 0 feet and 4 feet, another one when x is between 4 feet and 10 feet, and a third when x is, give me a little more space here, x is between 10 feet and 14 feet, and same thing here, a little more room, x is between 0 and 4 feet, another one, x is between 4 feet and 10 feet, and a final one, x is between 10 feet and 14 feet. And let's see. So this was 36 over 7 and 36 over 7x for the first zone. And then 36 over 7. Let's see. Just times x, 36 over 7 times x in that first zone of analysis. Then V2, I had 1/4 x squared minus 5x. So it gets complicated. 1/4 x squared minus 5x minus 5x plus 148 over 7 plus 148 over 7, and then the moment, oh, this is the long one, 1/12 x to the third 1/12 x to the third minus 5/2 x squared minus 5/2 x squared plus 148 over 7x, and then plus 1048 over 21. Lovely constant there. 1048 over 21. And then I would have, and maybe I could box this here. In the third zone, the shear is just equal to negative 27 over 7. And the shear here would be negative 27 over 7x plus 54. And notice we do have the derivative and integral relationships maintained. I can see this is the derivative of this is the integral of this, and so on and so on. And as a reminder, if we plotted all of these, now I don't necessarily want to plot all of these, especially this one, that would be a bit of a beast. But conceptually, you could do it just by taking ordered pairs or something like that. It wouldn't be too difficult to make a sketch, but this video has already gone on a lot longer than I'd originally planned. But my videos take longer than planned? Never. So anyway, that is the basic method of applying integration principles or the integral relationships between load, shear, and moment to analyze and get the moment in a shear and bending moment diagram, or get the equations for shear and bending moment in a beam. Now, once you've had these, you could probably use them for maximization. Like what I'd probably want to do is I could either set this equal to, if I wanted to know where the max moment is, I could take the derivative of each of these, or I could just look at these, set each of these equal to 0, and find for the points of any zero slope. Again, because shear is the derivative of moment, anywhere this is equal to 0, this is going to have a local max or local min. And those can then be places that you check for maximum moment. Because often what you're looking for in beam design is location of maximum shear. You're looking for, in beam design, typically you want the max shear and the max moment. And once you have the equations, then you can just apply basic principles of calculus to solve for points of maximum, or you can plot them on a calculator, or whatever you may wish to do. All right, so I do think this basically explains out, or just basically explains and draws out all of the various basic relationships between load, shear, and moment, and also explores how some of the details and difficulties of applying that in terms of working with zones of analysis, boundary conditions, all of that good stuff. So if you have any questions, please let me know. I'll be happy to answer them as I can. If not, I think this will do it for lecture 13. So instead of having the usual 3 or 4 portions, I think we're just going to have 2 really big ones for this lecture. And then in lecture 14, we're going to be getting to look at, we're going to start our look at centroids, our final sort of chunk of the course, looking at both, basically looking at cross-sectional properties in both centroids and moments of inertia. So we're going to start looking at centroids in lecture 14. All right, please let me know if you have any questions. I hope you found this illuminating, enjoyable, or at least hopefully didn't put you to sleep too much. But please let me know if you have any questions, and if not, I will see you soon for lecture 14. And as always, thank you.